In today's interview for EE News Europe, I'm meeting up with Wojciech Kozlowski, and he is the Quantum Communication Lead at SURF, and SURF is an IT research institute in the Netherlands. And our discussion, the focus of our conversation is on where we are in the whole transition of traditional internet, traditional computing, and quantum internet and quantum computing. Good afternoon, Wojciech Kozlowski. Do I pronounce your name correct?
Very nearly. It's Wojciech Kozlowski.
Okay. Sorry for that. I need to exercise on that, of course. But thank you very much for your time on this very interesting subject. I think the focus of our conversation is on quantum internet. Now we all know the internet, but we don't know quantum internet. So what do we need to understand to have a bit of an understanding of what quantum internet exactly is, and what we need to know for this conversation?
Yes, those are excellent questions. The quantum internet is fundamentally about the idea of using quantum physics for communicating with each other. So rather than just sending electrical signals or optical signals with each other, encoding bits, zeros and ones in our electrical and optical signals, we will be sending qubits, quantum bits, to each other, and we'll be using that for executing certain tasks. A very important phenomenon to understand for the quantum internet is it's a bit different from how our normal internet works, in the sense that when we think about the internet, we think about sending data from one place to another, and that's to a large extent what the very underlying technology does. What the quantum internet will do is, whilst it can send quantum data, its primary function will be different. Its primary function will be what's called a distributing entanglement. So first, what is quantum entanglement? Quantum entanglement is the idea that two particles are no longer independent of each other, regardless of the distance between them. So an analogy would be if you had two coins and you take them to two different cities, and then you flip the two coins in these two different cities, and they always land on the same side as each other. Okay. So every outcome is random, but they always land on the same side as each other. So they're not independent of each other.
And the quantum internet actually enables that. That is
precisely.
Okay.
Yes, and that is effectively what the quantum internet is. We will basically be distributing this entanglement, which allows this ability to combine systems distant from each other in ways that are not possible without quantum physics. And we will be using that to execute new applications that are not possible today.
Okay. So going back to the flipping coins, because I like that example. I'm in Barcelona. I'm not sure where you are. Perhaps in Delft or
in Den Haag.
Den Haag. Yeah. So I flip a coin, and then also on your side in The Hague, you flip a coin, and then something needs to happen between these two coins. They're in the air. They're going up, and then they need to come down. And how do they know exactly how to get on the same side?
Yeah, that's kind of the magic of quantum mechanics. It's
I was afraid you would be saying that.
Nothing strictly happens at the moment of the flip. A lot of things have happened before the coin flip. In order to distribute entanglement, the systems must somehow originate from the same place at some point. Okay. Which is where the internet of this comes, because the quantum internet will be responsible for sending the photons, which effectively, where usually what happens is you have two particles entangled, and then by sending photons over fiber, so photons are the smallest particle of light. As you send the photons, you kind of elongate this entanglement. So they start entangled next to there, and you elongate until it's Barcelona to The Hague. And then basically they are still, what happens is, according to quantum physics, they are just still the same system. They are not independent of each other, which is why they land on the same side.
Okay.
And if you go through, there's different ways one can think of this. The typical Copenhagen interpretation of this is basically that the moment we flip the coin, we're observing the system. So we make a measurement of the system. which what happens in quantum mechanics is the moment you observe or measure a system, you force it to choose a reality. So previously, it was in a superposition of two realities, one where both were heads and both were tails. But by flipping the coin and looking at it, we force it to choose whether it's heads or tails.
Okay.
So that's kind of it. To get deeper, what it means is you get deep into interpretations of quantum mechanics.
Yeah. And that is already achievable in what you're explaining now. The example of the flipping coins. I think what are the flipping coins in reality? Are these qubits or?
Yes, precisely. So
Okay.
this is all achievable. What it is in reality is usually, yes, some qubit. The simplest example is with actually photons. So you would start with a source of entangled photons. It would emit 2 photons in 2 directions. And then you would have them in a superposition of polarized horizontally or vertically or horizontally, or some other kind of superposition. And you would measure the polarization, and that's kind of the coin flip.
Okay.
So that's an example of it.
Yeah.
Polarization measurement is the.
Okay. Now, from my understanding, we're talking about a lot of research here. I understand that the flipping of the coin, to get back to that, is also very much very experimental, very fundamental thing to research. But I also hear you saying we're sending photons through fiber, and now that brings me a bit back to my original idea, because fiber, we're familiar with that. We already using fiber in today's communication, and we're already sending light signals, etc., over large distances. So that brings me a bit to my original question: how much of this high-end research is depending on what the existing communication?
Yeah. So yes, fortunately, actually, we can reuse our fiber infrastructure. So because fortunately, light happens to be the best carrier, one of the best carriers of quantum information. Guess it's coincidence, but it's very lucky for us. But other than that, our infrastructure will have to. So physically, we don't have to change. I mean, the wavelengths chosen for fibers are not actually the best for quantum. There actually is a necessity of quantum frequency conversion, and that is complicated. It's doable, but it leads to a reduction in efficiency. So it's not perfect, but it's still good that it exists. So it may be that the new fibers laid into the ground for the quantum internet in the future will be newer, will be different. But that's hardware-wise. But we will need a much more different software and protocol infrastructure on top of it.
Okay. So I also understand. We're using light now, photons, as most practical, most ideal communication form. There are other forms of communication thinkable.
Light is definitely. I mean, the medium is actually more important, and the medium. So fiber actually doesn't transport light at the speed of light, and it is very lossy. So first of all, it only transports it at 2/3 the speed of light, and it's very and it just loses a lot of photons. So you have to. So you're limited to a distance of like 100 kilometers or so in fiber. So what some people are doing is they're experimenting with free space. So they'll try to send the photons through the air, basically, or to a or from a satellite down to Earth, or to a satellite in space. Because transmitting photons through if you transmit photons to space, you only have about 10 kilometers of atmosphere to fight with. Okay. Then it's basically in a vacuum. So in a sense, it's much less lossy than
in the picture I have now. You say we're sending photons, let's say through fiber, but there's always sort of a delay. If I hear you saying some people are experimenting with free space or using a satellite, there's always a delay. How can you synchronize these two? Because the flipping coins, I can understand that it's a very basic form of communicating over long distance. And I can understand that that might be a sort of a foundation of, and to envisage how the quantum internet might work. But how can you synchronize that? How can you deal with all these different time delays?
It's actually interesting because there is definitely a lot of timing necessary in a quantum network, but not at that level of the flipping coins. So let me first say where timing is necessary, and then I'll actually I'll just in the coin flip experiment. What's actually interesting about the coin flip experiment is it doesn't matter who flips the coin first. They don't have to actually flip that coin at the same time.
Okay.
In this analogy, one Alice can throw the coin and see that it's heads, and then Bob's coin automatically also becomes heads, even if he looks at it much later.
Yeah. Okay.
So this part of the application of the quantum internet does not require timing. What usually requires timing is that it's still very important, and what usually requires timing is that currently there's two elements that require timing. One is we are not able to store qubits for a very long time. We have very short-lived quantum memories, if any at all, which means that if you actually do want to do such a coin flip experiment, by storing it in a quantum memory, you only have very little time to do it before the qubit is destroyed. Basically, it degrades over time.
I see a lot of research, I hear a lot of research. Sometimes I don't understand, but that is more my problem. But my next question would be, how will all this research actually get into reality? What will, in your opinion, be a sort of a first application where we say, okay, now we are using the quantum internet for this?
I would argue we already are, but yeah. So one of the earliest applications of quantum communication is quantum key distribution, which is the idea that we can use quantum effects to create encryption and decryption keys to secure our communication. And this is basically important because we already know that quantum computers will break our encryption, but also, very fortunately, quantum networks allow us to secure ourselves against quantum computers.
Okay.
So we can use quantum networks, quantum communication, to secure ourselves against the attack of a quantum computer, because the encryption and decryption keys are secure against the quantum computing attack. So that's the first application. We already know that. We already run that. SURF actually has a testbed running quantum key distribution between Amsterdam and Utrecht.
Okay.
And many other countries in Europe also have this, and the EU is investing heavily in this infrastructure.
Yeah.
The thing is, this infrastructure does not yet work with entanglement. We're still sending just photons on a fiber in one direction, so we're not doing everything I've described, but we're just sending photons and doing something slightly different. So it's a very limited quantum internet. One could argue it's a proto-quantum internet. It has a lot of similarities because it's still single photons, it's still quantum, but you can only do this quantum key distribution. The next generation of the quantum internet needs a bit more time because and it's going to come in stages. We can actually already generate entanglement between quite distant locations. In fact, there is a vendor, at least one in Austria and one in the States, who can actually sell you equipment for a data center that will do that. And you can send photons that are entangled towards each other. Okay. But that's just photons. Yeah. There's no quantum memories involved, which means the applications there are limited. So there are some basic things we can do with this that are beyond quantum key distribution, but nobody has actually... There have been some demonstrations of it. For example, in Italy or Spain, they've demonstrated that you can... or Portugal, somewhere there. They've demonstrated that you can execute another quantum protocol called quantum oblivious transfer with the same hardware. And why is that? What does that do? It allows you to do what's called secure multi-party computation, which is the ability to compute things at two locations without the locations revealing their inputs or outputs to each other.
Okay.
Sure. I do have to say this is already possible without quantum. The quantum aspect just gives it security against quantum computers.
Yeah.
So that's where we're at today. That's today. So in short, we can already do some things. We're already trying some things. They're very limited. The next, how to go more from research to we need to develop more technology for the end nodes. So you already saw an end node at the event.
Yeah.
They're very limited. They cannot hold too much qubits in memory. We need bigger nodes to hold bigger memory, or yes, basically to have more complex applications. And we also cannot do long distances as well.
Okay.
For long distances, we need a technology which is called the quantum repeater, and that's also under development.
Yeah.
That's currently the situation.
Okay.
And just to wrap up this reply, by 2029, what we expect, what Quantum Internet Alliance has promised and expects, is to demonstrate the ability to connect two metropolitan-sized networks, so about 50 kilometers in size from one end to another, over a 500-kilometer backbone. So that's what we should be expecting, and one of the nodes should have up to 20 qubits or something like that.
Yeah.
This is what we can expect by 2029.
Okay.
So that's where we are.
So 4 more years.
Yeah.
Now, the other question, I'm not sure how relevant this question is, but today's internet, of course, has to do with the electrical signals, etc., but also very much the protocols and the way these signals are distributed, etc. What is your first guess on in the future of quantum internet? Will it be compatible with today's internet? Will it support a sort of a protocol which is comparable to what we know now? Is it open? Or is it very much specific and has its own identity?
First of all, So first of all, quantum internet will enhance the existing internet. So what we're doing right now with the internet will stay. It's not going to replace it. What it's going to do is we're going to now basically be adding quantum links to all our existing links to have a quantum internet alongside the internet because it will add a new functionality, new applications that were not possible before.
No.
Now, in terms of protocols, it's perhaps a bit hard to say. The history of the internet is interesting because it somehow naturally evolved into this set of open protocols. And the internet that was built in the first days is not the internet we'd built today. And we know that because they're trying to solve some of the problems of the early day of the internet. For example, it was built assuming that everybody participating in the internet is trustworthy, or they're not going to be malicious. That turned out not to be true.
Okay.
So now a lot of the infrastructure, there's a lot of work on upgrading the infrastructure to support the idea that actually a lot of users are malicious.
Okay.
But we will likely, I think we will end up with open and standardized basic protocols for a very simple reason, is because there's already some work on standardization within this quantum key distribution networks. And while each vendor would like to do his own thing and they'd like to keep things proprietary and secret and sell it just to only their customers, and the vendors are not interoperable, the telecom operators and the governments that pay money for this infrastructure very much essentially forces the vendors to support interoperability. And so the vendors are working on figuring out how to achieve this interoperability. It simply comes from the fact that, for example, when we received some subsidies to deploy this testbed network, and SURF reacted to this by saying, well, we wanted to be interoperable with multiple vendors. So condition of our project was that we'll get 2 vendors and we'll need to make sure they work with each other. The vendors themselves didn't work with each other, so SURF invested some of its work into writing software to make them work with each other. But now I think the vendors are naturally converging on this because there's further investments coming from the European Union to connect multiple countries to each other, which will require all of these vendors to talk to each other. So I think we will end up with an open set of protocols and standards on that front. In addition, they will hopefully be also more secure than the first internet. There's a big gap between today's quantum key distribution networks and the next generation entanglement networks. I do think one will evolve into the other. It will be hard work, but yes, that will happen. And basically, we're there. We're deploying infrastructure across Europe, and I think it's a good opportunity to be hopeful about it.
Okay. Okay. Well, thank you very much for your explanation. I think that was great. It opened my eyes. So that, and I've been learning a lot this afternoon. Thank you very much for your time. And I hope that somewhere in the future through entanglement or by flipping coins or whatever we might do, but we can connect again and have a further discussion on this subject.
Yeah, let's hope so.
Thank you very much for your time.